Hello everyone, welcome to our differential equation class. In this video we introduce simple boundary value problems. We are going to start with an overview of the material covered in this course because in the previous video we finished a main subject, which was to understand how to find solutions of first order systems of nonlinear differential equations. And now we start a new subject, which is how to solve a partial differential equation. So we are going to talk a little bit about that in this overview, and then we go to the material in this video, which is to introduce boundary value problems. And these are simple boundary value problems called 2-point boundary value problems, because the boundary where we are going to work is actually points. So we are going to work in an interval, and the end of the interval in a variable that we are going to call x. The end of the interval, for example 0L, these are going to be the 2 points where we are going to introduce boundary conditions. So that's why these problems are called boundary value problems. And then we are going to compare what we know about initial value problems with what we can know about this new type of problems, boundary value problems. So that's the plan for today. Let's start with an overview of the materials covered in this course so far. We started in chapter 1 studying first order differential equations. Then in chapter 2 we moved to second order differential equations, and we learned how to solve it in one way in chapter 2 and using the Laplace transform method in chapter 4. Then in chapter 5 we introduced matrices and matrix algebra that we needed in chapter 6 to understand how to find solutions of first order systems of linear differential equations. And all that was used in section 6.5 and 6.6 to understand how to find qualitative properties of solutions to first order systems which are nonlinear. And that was more or less the end of that part of the course. And now we start a new part in chapter 7, the last part of our class, where we are going to try to solve a partial differential equation, and among all possibilities we chose only one, the heat equation. So that is our problem now. We are changing subjects from what we did so far, and the rest of the course is going to be about solving one partial differential equation. The differential equation we are interested in is the heat equation, which is the equation that describes how the temperature of a solid material, for example a metal bar like this rectangular bar, how the temperature changes in time and in position in a solid material. The equation we are going to solve is this equation here, which is called a partial differential equation because the unknown function, which is the function temperature, depend on two variables instead of one as we have been working so far. Now we have two variables. One variable is time, the other is position along the bar, and the equation relates partial derivatives with respect to time with partial derivatives with respect to position. Because of that, the equation is called a partial differential equation. And we are going to try to solve this equation knowing what is the initial temperature of the bar. So we need to know the function tau, which is a function of x, the initial temperature of the bar, so the temperature at time t equals 0. But that is, we are going to see that this is not enough to solve for the temperature. We need more information about the function temperature, and this more information is given in terms of boundary conditions. So boundary conditions are what is the temperature of the bar on the boundaries of the bar, so on the surface of the bar. I'm going to reduce the problem to 2 points. So the boundary, knowing the temperature of the of the bar at 2 points at x equals 0 and x equals L for all times, we are going to see that it's going to be enough, knowing that, and knowing the initial temperature of the bar, to find the solution of the heat equation that describes how the temperature of this bar changes as a function of time. So this is the new problem we want to solve, we want to study, and to do that we need to learn a few things before we can actually tackle that problem. One of the things we need to understand is, well, what is a boundary value problem for an ordinary differential equation, and then understand that this type of problem may have infinity many solutions, and from this type of problems we are going to define a new problem that we are going to need to solve the heat equation, which is the eigenfunction problem, which we are going to talk about in a future video. Once we understand what the boundary value problem is and an eigenfunction problem is for an ordinary differential equation, then we are going to move on into what is called a Sturm-Liouville problem, which is essentially, or Sturm-Liouville theory, which is essentially to understand what are the properties and the behavior of solutions to a particular type of eigenfunction problems. The particular type that is going to show up when we solve the heat equation. At this point, we are going to do a little bit of study a particular case, which is called the Fourier series, which is widely used everywhere in science and engineering. After that, we are going finally to solve the heat equation using what we know about boundary value problems, eigenfunction problems, and their properties. So that's the plan for the last part of our class. Let's introduce the main subject of this video, which are boundary value problems, in particular what they are called 2-point boundary value problems. And here they are. First of all, we are going to introduce an operator. The operator is going to be the second order linear operator, the usual operator we've been working in chapters 2 and 4. A second order linear operator, which is the operator acting on a function y, is equal to the second derivative of y, then plus some function that is, now we are using the variable x, we go over that in a minute, y, times the derivative of y, plus some other function times the function y. So this is a linear operator we are familiar with, and a 2-point boundary value problem is the following: is to find a function y of x, solution of this differential equation. You see the operator is on the left side. Solution of this differential equation satisfying what we call boundary conditions. And what are boundary conditions? They are conditions of this form, which looks very complicated. So what we have here is b1, b1 tilde, and d1. These are given constants. And also b2, b tilde 2, and d2, they are also given constants. So these are given in the problem. And here we have the value of the solution we are looking for at 2 different points. x1 is different from x2, and here is the values of the derivatives at x1 and x2. So what this problem is a 2-point boundary value problem, is to find a solution of a differential equation, and this solution, actually we know for constant coefficients how to find the general solution of the differential equation. So we know this part already from previous videos. When these functions are constants, at least in that case. And we know how to find all solutions of this problem. And now we need to find one, among all these solutions, we need to find the solution of the problem, y of x, that satisfies these extra conditions that we call boundary conditions. So that is a boundary value problem. We are going to see examples pretty soon, and then we can come back to this definition. A few remarks before we go to an example. And the first remark is that, as you notice, we are using the independent variable, the name x instead of the variable t. And this is for the main reason is that in applications, when we try to solve boundary value problems coming from physics, the meaning of the independent variable usually is going to be position instead of time. So that's why we change to x. The boundary conditions are set, if we mentioned before, but we remark it, are set at different points. So x1 is different from x2. This is what we are saying here. So this condition, these are the condition on the function and the derivative that of the solution we are looking for, evaluated this equation at x1. And this second equation, they are with different constants, but this equation is evaluated at x2. And these 2 points have to be different in order that the conditions are called boundary conditions. We are going to see example of that in a minute. And most of the time, although here we introduce the definition for a general second order operator, most of the time we are going to be working with a very simple operator, which is the second derivative of y plus a constant times y. So just to keep in mind that this is our main operator that we are interested in. Why this operator? Because this is the operator that we are going to face later on when we try to solve the heat equation. Okay, let's see examples of boundary value problems and try to understand what we have over here, which is the new part essentially of the concept. So let's see a few examples. A boundary value problem is to find a function y, and let me emphasize now that the variables we are using is for the independent variable is x, so y of x. Solution of, as we mentioned, this is the main equation we are interested in, with the boundary conditions, let's say at x equals 0 and x equal 1. As you see, x1 is different from x2, 0 and 1. And what boundary conditions are these? Well, we have many type of boundary conditions. The first one is what we call Dirichlet boundary condition, which is to find a solution of this equation that satisfies that the solution at 0 takes a particular value and the solution at 1 takes some other value. So these are 2 conditions on the function y. Recall why we need 2 boundary conditions. For the same reason, we needed 2 initial conditions when we solve this equation. For example, initial position and initial velocity. These were initial conditions when we solved this equation in the previous video. We needed 2 conditions because the general solution here has 2 arbitrary constants, C1 and C2, and these 2 constants are fixed with the values of the initial position and the initial velocity in an initial value problem, where we have initial conditions. Well, here we still have the same differential equation, so we still going to have 2 arbitrary constants in the general solution, so we need 2 conditions to fix C1 and C2, and now they are going to be different conditions. They are going to be the function, the value of the function at one side of the interval and the value of the function at the other side, but still 2 conditions to fix 2 constants in the general solution of the equation. Now, this type of boundary conditions, as we see here, they include only the values of the function, not the derivative. But this is a particular case of these boundary conditions here. We just need to choose this constant b1 tilde equals 0, so this is not going to be here. b2 tilde equals 0. This constant equal 1, so it's 1. This constant 1, and then the values of the function are given. I try to look for a solution such that at x1 the solution takes some value, and x2 the solution takes another value. This is what we are doing here, and as you can see, this is a particular case of the condition above, when b1 and b2 are 1, the tildes are 0, and the d's that we mentioned up there, they are 2 and 3. So this is a complicated way a more general way to write that boundary conditions that, for example, they reduce to, for particular value of the constant, to this simple boundary condition. Because this boundary condition contains only the function and not the derivative, because we killed these terms here. This condition actually is called Dirichlet boundary condition because it was Dirichlet who solved a problem with similar boundary conditions for the first time for an equation similar to the heat equation. Another particular case of the boundary conditions above is the Neumann boundary conditions, which are conditions, as we see here, for the derivative of the function, not the function. So we are looking for solution of these equations such that the derivative of the solution at the initial point takes a particular value and the derivative of the solution at a different point takes some other value. These are Neumann boundary conditions because Neumann was the first person that solved a similar problem with conditions that involve derivative of the unknown function in an equation similar to the heat equation. You can see that this is the particular case of this boundary condition when this coefficient is 0, this coefficient is 0, this is 1, this is 1, and I put here 2 and 3. So these conditions here. And of course we have mixed conditions, for example conditions that include the function and the derivative. So in the first condition at x equals 0, for example, we can have a condition only for the function, and then in the other condition at x equals 1 we can have a condition on the derivative of the solution. This is mixed because one condition contains the function, the other contains the derivative. Or we can have it the other way. The first condition contains the derivative, and the second condition contains a condition on the function at x equals 0 and x equals 1. Both are called mixed boundary conditions. So all these are particular cases of the condition above. And the condition above contains something more complicated, which are called Steklov boundary conditions, although in the literature they are usually called Robin boundary conditions. The beef I have with Robin is that Robin never solved a problem with this type of boundary conditions, and actually Steklov did, so it's better to call them Steklov boundary conditions. And these are conditions that contain both functions and derivative on each equation. So this, you see, we are looking for a solution of the original differential equation that this combination of function and derivatives at 0 is fixed by this value, and this other combination of function and derivative is fixed by this other value. So in our class, in these videos, we are not going to see Steklov boundary conditions. We are going to study these 4 boundary conditions, the Dirichlet, Neumann, and the 2 mixed boundary conditions of this form. These are the conditions we are going to study, but all these conditions are included in this definition. Now let's compare initial value problems with boundary value problems. So if you recall, in previous videos at the beginning of this class, of this course, we introduced initial value problems for a particular type of differential equations, and now we want to compare those type of initial value problems with the boundary value problems we introduced today. So this is the definition of an initial value problem in a particular case. So an initial value problem is to find the function y of t. Recalling initial value problems, the name of the independent variable is usually t because it represents time. So we want to find a function y of t solution of, let's say, this equation that could represent the motion of a mass spring system. And from all the solutions of this equation, we want to find the solution that satisfies a particular set of initial conditions, which are essentially the initial position should be a particular position, and the initial velocity should have a particular value for the velocity. These are initial conditions, what we call initial conditions, and notice that both equations are evaluated, have the solution evaluated at the same value of the independent variable, which we call the initial time. So the main characteristic of an initial value problem is that the extra conditions are conditions evaluated at the same value of the independent variable that we call the initial time. So a few remarks: the variable t has a meaning of time, that's why we use that name for the independent variable. The variable y usually has meaning of position, because usually this equation comes from Newton's equation of motion, of the motion of a point particle. So y is a position, and the initial conditions, as we mentioned before, are the initial position and the initial velocity of that particle. That was an initial value problem. Now let's compare that with a boundary value problem, and from all possible boundary value problems, let's choose a Dirichlet boundary value problem just to compare the two problems. In the boundary value problem, we need to find a function that we call y of x, solution of same differential equation. Notice it's the same differential equation. That's not what is different. What is different is in the condition we want that solution to satisfy, that which now are of this form, and they look very similar. The first condition is the value of the solution at some point of the independent variable is fixed, and then the value of the solution at the different point is also fixed. That is what we call Dirichlet boundary conditions. In this case, the name of the variable, we change it from t to x, because usually this type, although the equation is the same, the meaning of the equation is different. In the initial value problem, usually this equation comes from Newton's equation and the variable is time. This equation here comes from other equations. In particular, in our problem, is going to come from the heat equation, and the variable, then the independent variable, is going to have meaning of position. And in that problem, in the heat equation, the y variable is going to have meaning of temperature, but in different problems it can have any meaning, so it could be anything. In our case, it's going to be temperature, so temperature as function of position. And the boundary conditions, what they are? Well, in the case of the Dirichlet boundary conditions, this condition fixed the temperature at two different places. So that is a boundary value problem compared with an initial value problem. What can we say about the solutions of these two problems, initial value problems and boundary value problems? Well, for initial value problems, we have proven many theorems, and here is one of them that says the following. The initial value problem for the function y of t given by solution of this differential equation, recall this equation essentially is the motion of a mass spring system, satisfying initial condition given by initial position and initial velocity. Let's put y1, or I'm gonna change a little bit the names because I don't like it. y0 here, oops, that's the wrong color. y0, and let's put here v0 because it has more meaning as velocity. So initial conditions given by initial position and initial velocity. Well, this problem we have seen many times that it has a unique solution, the function position, a function of time, for every choice of the initial conditions, which are now called differently. Now they are called initial position and initial velocity. No matter what initial position and initial velocity you choose, you always get one motion for the spring. So that is what we knew. Now, what happens with boundary value problems? One could guess, well, the same thing, isn't it? If we change this, since the differential equation we are solving is the same differential equation, changing these conditions to something else, for example, to these conditions is not that important, and we still have unique solutions for whatever boundary condition we give. Well, that is not what happens. This is what happens. Consider the boundary value problem for the function y of x given by the same differential equation as before. And now we solve this problem. We obtain the general solution, y of x general solution. We know how to do that. And now we need to find among all these solutions the solution that satisfies one of the following boundary conditions. That recall we introduced conditions of the form Dirichlet, Neumann, mixed, or mixed. There are two types of mixed conditions. So for each of these conditions we have a different solution. So the boundary value problem with Dirichlet conditions means to find from all the solutions of the differential equation the solution that satisfy this condition. So the values of the function at two different points are given. Recall Neumann is a condition on the derivatives of the function. And recall mixed is a condition on one side for the function and the other side for the derivative, or vice versa. These are different types of problems. So consider all these four problems. These are four boundary value problems. Okay. Now, suppose that we called r plus and r minus the root of the characteristic polynomial. Recall how we obtain this characteristic polynomial. We look for solutions of the form exponential rx. You put that into the equation and immediately you get this equation equals 0 for the roots. So for this polynomial, so let's suppose r plus and r minus are the solution of this equation, the roots of the characteristic polynomial. Then actually we have two different cases. The first case is that if the constant k, this constant k that shows up in the equation, is negative, then we are going to see that when you move it to the other, if this is negative, you move it to the other side of the equation 0 and it becomes positive. So the roots are going to be real and different. And in that case, the boundary value problems, all these boundary value problems, the four of them, have a unique solution no matter what do you choose here for the constant d and for the value of L. All the problems have a unique solution. This is essentially the same thing as what happens for initial value problems. Unique solutions. But this is only when k is negative. In the initial value problem, the unique solution is for k negative and k positive for both cases. Here not. For k negative, we have unique solution. But what happens when k is positive? Well, something else happens. When k is positive, then we are going to have the characteristic polynomial with imaginary roots, so complex roots, pure imaginary. And now, the case, the situation is very different. Depending on what do you choose for these constants, and what do you choose for the value of L, you may have one and only one of the following results. You may have a unique solution, or if you change the values of D and L, you may have no solution, or you may have infinitely many solutions. That depends on what do you choose for D1, D2, and L. So this case, when k is positive, is very different from initial value problems. And actually this is the case that is going to show up when we solve the heat equation. So what we are going to do now is we are going to prove this theorem. But you see there are many cases. We have to prove this theorem for Dirichlet, then for Neumann, then for mixed 1, then for mixed 2, and we have two cases, this constant k negative or this constant k positive, so it's a lot of work. To save a little bit of work, we are going to focus only on this case, and we're going to prove this theorem only for Dirichlet. And then once you see how it's done, you can actually, as an exercise, do the calculation for the cases of Neumann and mix 1 and mix 2. So that is our plan. Prove this theorem for Dirichlet boundary conditions. Okay, let's prove this theorem for proof only for Dirichlet boundary conditions. So only for Dirichlet. Boundary conditions. The other part is left as an exercise. So what is the equation we are solving? We are solving the differential equation y double prime plus a constant y equals 0. How do we solve these equations? Well, in chapter 2 we realized that if we try solution of the form exponential rx, recall x is our variable now, we are going to end up with the characteristic equation r squared plus r plus k equals 0, something like this. And you see the solutions here are going to depend on the value of k. So solutions obviously depend on the value of k, because usually we have a fixed k, now we have an arbitrary value constant for k. So then we have several cases, and the main case that we have in the theorem is case A, when k is negative. Okay, let's start with that, k negative. So let's write k as negative some number square, so that we see the k is negative. So now if we study that into the characteristic equation, we get minus v squared equals 0. We move the v to the other side, and we are going to get that r squared is equal v squared. And from here we get that we have two roots which are real plus minus v. So real roots and real, and actually v plus is positive and v and r minus is negative, and actually, well, they are given by this expression, one positive, one negative. Okay, what is our general solution? General solution, well, is the function y of x given by some constant c plus exponential vx plus c minus exponential negative vx. That's the general solution, and now we introduce the Dirichlet boundary conditions. And what are the boundary conditions? Well, d1 is the value of the solution at 0, so we look for a solution that satisfies this condition, and also the other condition that d2 is the value of the function at L, where L is positive, so two different values for the independent variable. So what is the first condition? The first condition says that d1 is going to be equal, of course, the solution at 0. We have our solution here, so we evaluate it at 0, and we get c plus plus c minus. d2 is the other condition, which is the solution at L. Okay, now what are we going to get? We are going to get c plus exponential vl plus c minus exponential minus vl. Okay, and now what do we need to do? We need to solve for c plus and c minus. We need to solve the following system. We need to solve the system given by 1 exponential vl exponential minus vl. This is a matrix acting on the coefficients vector c plus c minus. I'm using what we have learned from linear algebra to solve this problem, d1, d2. So you see we have something of the form a matrix A, acting on the vector that we are looking for, the vector with coefficients vector C, equal that, the vector D. And we need to solve this problem, so we don't actually need to solve the problem, we need to know if the problem has solutions or not. Well, that reduces to the question whether the matrix A here is invertible. If the matrix is invertible, then we multiply by the inverse and we get our solution. And we are going to get a solution no matter what you put here. So that if the matrix is invertible, then there is a unique solution, C plus and C minus, for whatever constant you put here. You put there. Therefore, there exists a unique solution for the differential equation, because there is a unique solution for the coefficients go here, and you get a unique solution for the differential equation. How do we know if this matrix is invertible? Well, we compute the determinant. We compute the determinant of matrix A, which in this case is going to be exponential negative VL minus exponential VL, isn't it? Product of these two coefficients minus these two. Well, but this is nothing more than 1 over exponential VL minus exponential VL. And you see here, for any V different from 0, this is different from 0. For any V different from 0. So that's it then. The matrix A, because the determinant is different from 0, this implies that the inverse exists. We don't need to compute it, we just know that exists, and then we are done. Then y of x exists, the solution differential equation exists, we already have proven that exists, and is unique. And this is what we say here. Whenever the k is negative, there always exists a unique solution, and here we have proven why. So now we move to case B. Let's go here, case, here, case B. This is the interesting case, case B. And we were in case A, now case B. K positive now. Okay, when k is positive, let's write k as a square, w square. Just do not get confused with the b we used before. So what we need to solve is the equation r squared plus w squared equals 0. And you see what is going to happen now. R squared is equal a negative number. So the roots plus minus are going to be plus minus wi, which are complex. Okay, complex roots. So what is the general solution in this case? Well, the general solution of the differential equation is y of x. As you should know, this is c1 cosine of omega x, recall x is our variable now, plus c2 sine of omega x. So that is our the solution of the differential equation. And now we go to the Dirichlet. Boundary condition, which, if you recall, d1 is the function at 0 and d2 is the function at L, for an arbitrary L positive. So I fix a value of L. So what is the first boundary condition? The first boundary condition is just that d1 is the solution at 0, but 0, this disappears, this is 1, the cosine is 1, and we end up with c1. Okay, what is the other boundary conditions? d2 is c1 multiplied by the cosine of omega L plus c2 sine of omega L. Okay, so now we need to solve this system for C1 and C2, and the system is nothing more than we put a 1 here, a 0 there, then we put a cosine of omega L over here, a sine of omega L over there. This has to act on the constant C1, C2, and the result has to be the constants D1, D2. Well, here we have our matrix A as before. Now A is different because K is different. So this is our matrix A. This is the same vector we introduced before, the vector with the constant C. And here is the vector with the constants D. And now we have the same question as before. Is matrix A invertible? If it's invertible, then we can solve for the constant, and then there is a unique solution for the constant, and therefore a unique solution for y. Is that matrix invertible? Well, we need to compute the determinant of that matrix, but the determinant is the product of these two coefficients minus 0. So is the sine of omega L. Okay, so now the situation is very different because sine can vanish. Before, in the other case, we got something that is always different from 0. But now, this is not the case. Now we have two possibilities. Suppose that the values of k we have chosen and the value of L we have chosen is such that the sine is not 0. Then, well, then the matrix is invertible as before, then there exists a unique solution for the constants, and therefore there is a unique solution for the differential equation. And then we are in case 1b, which is, in the theorem, this case here. K positive, sometimes there is a unique solution. And now we know exactly when sine of the square root of k multiplied by L is different from 0. When that happens, here is k and L is from the boundary conditions, you have a unique solution. What happens if it's not that case? What happens if sine of W times L, if that sign is 0? It could happen. You can choose a value of k such that the square root of k multiplied by L is a multiple, is for example a multiple of pi. Then that is going to be 0. And then the matrix is not going to be invertible, and then you can check that two things can happen. Either there is no solution for C1 and C2, and therefore no solution for the differential equation, which is the case 2b we mentioned before, or one of the constants is not fixed by the equation, one constant is free, and then you have infinity many solutions for the constant, which means infinity many solutions for the differential equation, which means is what we say in case 3b. And that's the proof of the theorem. The proof of the theorem has little to do with the differential equation, because we know how to solve the differential equation, here it is, and a lot to do with algebraic calculation to find the constants in the expression of the general solution. We end this video with an example where we are going to do the calculations in the theorem above for a particular case. So this is our example. Solve this differential equation. Notice that here we are choosing k to be 1, which in particular is positive, so we are in case b in the theorem. So solve this differential equation for each of the following 3 Dirichlet boundary conditions. So here we have one choice of the value of L. Here L is pi. Here we have a different choice of the value of L. L is pi over 2. And here we are back to L equal pi. And then we have different values for the constant. These are the constant d1 and d2. Well, we choose the same values here, and here is something different. And also notice that the first boundary conditions in all these three problems is the same, to make things simpler. Okay, let's solve this problem. Let's see that in one case, I don't know which one, in one case we are going to have a unique solution, in another case we are going to have infinity many solutions, and in the other we are going to have no solutions. Let's see that. Solution here. Over here. So how do we solve this problem? Let's notice that this is the equation. What we mentioned before, we are going to put it in writing. This is an equation of this form, where k is actually equal 1. So we are in the case k positive, and therefore case B in the theorem. Which is the interesting case. Otherwise, we are going to get unique solutions always. So let's put that in writing. Case B in theorem above. Okay. So let's solve the problem now. So how do we solve this problem? Like we did in the theorem, we have this equation y double prime plus y equals 0. We look for solutions y of x of the form exponential rx. That is going to give me an equation for r, which is going to be very simple: r squared plus 1 equals 0. So from here we are going to get that r squared is actually negative 1, and of course r has to be plus or minus I. Okay, complex. Good. So what is the general solution? General solution of the differential equation, well, it's going to be a constant multiplied by the cosine of x plus another constant multiplied by the sine of x. Alright, this is the general solution for all differential problems that we need to solve. So now we impose the boundary conditions. The first boundary condition is here, boundary condition number 1, which is the case A. Recall, we say that 1 has to be the function at 0, and the other is 1 has to be there. Okay, I got lost. This one, and the other has to be 1 has to be the function at pi. Okay. What is the first condition then? So let's write it down. 1 is the function at 0. But what is the function at 0? We put 0 here, 0 there, and we are going to end up with C1 multiplied by the cosine of 0 plus C2 multiplied by the sine of 0. But we know very well that this value here is actually 0, and this value here is actually 1. So this equation is nothing more than 1 is equal C1. We determine C1 with the first condition. The other condition is 1 is equal the solution at pi. Okay, we should be able to find the other constant. So we have C1 cosine of pi plus C2 sine of pi. Sine of pi here. Alright, but we know very well that the sine of pi unfortunately is 0, and the cosine of pi is actually negative 1. So we end up with the equation 1 is equal negative C1. So what is it? Is C1 equal 1 or is C1 equal negative 1? It cannot be both. So because it cannot be both, that means only one thing. And that is that there is no solution. There is no solution for the constants, and therefore there is no solution for the differential equation. And you see what happens. Sometimes the boundary condition could be contradictory. That never happened with initial value problems, but with boundary value problems you can put conditions that determine that assign two different values to the same constant. Therefore there are no solutions, like here. Okay, so that's why we don't have solution, because we have contradictory conditions for the same constant. Okay, we learned something from the example, and now let's go to the next problem, which is the problem with boundary conditions B. And now we have boundary condition y1 is equal y at 0, and then 1 is equal y at a different point, at pi over 2. Before it was pi, now it's pi over 2. So this part of the calculation is going to be exactly the same, isn't it? Because it's the same condition. Copy. Let's put it here. You see, this part of the calculation is the same, because we have this condition is the same. So evaluate at 1, at 0, we need to evaluate at 0. This is 1, this is 0. We get that. Now let's put this condition. This condition is also 1 equal the function at pi over 2. Now, oh, that's different, because we have C1 cosine of pi over 2 plus C2 sine of pi over 2. And now what happens is the following. This number here is actually 1, and this number here is actually 0. So we are fixing or determining the, let's put it like this, the other constant now, which is C2. So you see we have one value for C1 from one condition, one value for C2 from the other condition. These conditions are good in the sense that they fix both values of the constant uniquely, and then what we have here is a unique solution. And this is one of the cases in the theorem. Now what happens with the last boundary condition? Let's put here boundary condition C. And what was boundary condition C? Well, this condition was the same, y at 0 equal 1, and the other, that condition, and the other is -1 is the solution at pi. Okay, -1 is the solution at pi. Okay, again, this condition is the same as this condition, so of course we can copy what we did for that condition, and that condition determines the constant C1. Now let's do the other condition. The other condition is -1 is equal the solution at pi. If we evaluate the solution at pi, we are going to have cosine of pi here plus C2 sine of pi. But we know very well that the sine of pi is 0 and the cosine of pi is -1. So this equation implies that -1 is equal negative C1, or what is the same, 1 is equal C1. So we obtain exactly the same equation that from the other boundary condition. This equation and this equation, both boundary conditions, this and that, give you the same value for the constant and nothing for the other constant. So what happened with C2? It's not fixed by this condition, so it's totally free. And what all this says is that, well, we have infinity many solutions. Because C1 is fixed, but we have one solution for each value of C2. So here are the solutions. The solutions are, here, there we are, y of x. Well, C1 has to be 1, so we need to put a cosine here of x, and then any constant times the function sine of x. And these are the infinity many solutions. So this is how boundary value problems are different to the solutions are different to initial value problems, in the sense that you can have unique solutions, infinity many solutions, or no solution at all for some differential equations. In this case, differential equations for this operator where k is positive, you may have any of these cases that we never saw before in an initial value problem. So this is a good place to stop. See you guys in the next video.